So, Maddie, I want to talk about work. In physics, work has a very specific meaning. In English, when you say, I'm doing work, usually you mean, I'm doing something that makes me physically tired. That is not the physics definition of work. I'm going to have to gently nudge that out of you. In physics, work is not doing something that makes you get tired. Instead, work is done on an object. Eli, who's not foolish looking at his phone, is going to pay attention here. So you don't do work, Justin. You do work on something. If work is to be done on an object, two things must happen. Number one, a force must act on the object. And number two, the object must move through a distance, and here is the condition, in the same direction as the force. Work is a scalar. No more let forward be up be positive and down be negative, or north be positive. We were vectors in the last unit. Work is a scalar, and it's calculated by work equals force times distance. We use a capital W for our abbreviation for work. I've gone on my rant about how we are running out of letters because capital W is also west. And capital W is also watts. It's a unit of power. So if you see a W by itself on the left side of an equal sign, that's work. And it's force times distance. Force is a vector, but in this case, all we do is we say, are the force and the direction in this, are the force and the distance in the same direction? Then if you've made that check, then it's just the magnitude of the force times the magnitude of the distance. What would the units be? What do I measure force in? What do I measure distance in? So technically, work is measured in a Newton meter, but it's such an important concept, we've given this a name. We call this a joule, symbol capital J. 1 joule is how much work it takes to apply a force of 1 Newton and move an object 1 meter. There's another restriction. In this equation, the force has to be constant. If you have a changing force, we're going to have a much more complicated definition. In fact, in Physics 12, if you take Physics 12, near the middle of the year, we'll start looking at rocket science. And as you go further from the Earth, what happens to the force of gravity as you travel further and further and further and further from the Earth? Is it always the same? It gets weaker. We're going to have a much more complicated definition of work. I make the joke in Physics 12, this is the most work you're going to do because it ends up being about 9 or 10 lines. Just no workaround. And no workaround. Another good joke. There's just no way around it. We'll have a more complicated definition. I'll introduce you to that more complicated definition this year. You might wonder why I'm doing that this year. It's for rocket science. Example 1. Mandy, what does example 1 want me to find? Stop. There you go. So, you know what? Since we're learning something new, let's do our systematic defect approach. Let's write down W equals question mark. I see 12 kilograms. I see 9.5 meters. I don't know if I see force. Okay, well, you know what? Let's write down work equals force times distance. I'd like you to imagine that I'm lifting something. Get the free body diagram, get the obvious one. What are the forces acting? Get the obvious one. Gravity down. If I'm lifting something, the force that I'm lifting up with is the same as... So I'm going to write mg for the force. they're in opposite directions, but that's okay because the distance that I'm lifting it is vertical and the force that I'm exerting is vertical. Although mg is down, I'm not actually saying that the work done lifting is mg times the distance. I'm saying it's the force the same size as mg, so I'm going to use that. Is that okay? It's a bit of a long argument there, but I got to be nitpicky, Mackenzie. Is that all right? If you're lifting something at a constant speed, and let's pretend we are, so we don't have a changing force. If you're lifting something, the force that you're lifting with, you're canceling out gravity. So we're going to say this. The work, and do me a favor, can you underline the word lift? When you're lifting something, the work is the force of gravity, and instead of a distance, let's call it a height. You may, if you look on your green sheet, see MGH described slightly differently later on. That's a preview of coming attractions. But for now, Mandy, what's the mass? G. Do you still have this memorized? It's been a while. And are we going to use the negative? We're in Scalarville, so 9.8. Don't care about negative. 9.5. 12 kilograms, by the way. This lead mass that I have hidden over here that I brought out every so often, it's right around 12K. It's about 25 pounds. 9.5 meters, that's about that flight of stairs in the back corner. This would be how much work it would take for you to carry that lead weight up that flight of stairs. And because I'm giving you a new concept, this gives you an idea of what a big or a small number. All of you could probably do that pretty easily. If I asked you to do it, Emily, 50 or 60 times in a row, you'd be getting tired. But certainly once, if I said, as a favor, could you carry this upstairs to so-and-so? I think every one of you would, it's a little heavy, but I can do it. What do you get? Emily, sorry, Hannah, what'd you get? 1,117.2. I'll go, I don't know, I'll call it 1,120 joules. Basically, 1,000 joules is a bit of an effort, but not much work. Meh. Cross out the word coal. Evan. Evan, could you stand up, my friend? Behind you, there is a section of wall between the bulletin board and the poster. Could you push against it as hard as you can for 12 seconds, please? Hard. 1. Keep going. 2. 3. Keep going. 4. 5. Keep going. 6. 7. 8. 9. 10. 11. 12. Are you tired? If I asked you to do that for 30 minutes, and for 30 minutes you did push as hard as you could, would you get tired? Tiredness is not work. Did you do any work? Did you apply force? Yeah? Did the wall move a distance? So was any work done on the wall? Supposing you're pushing a box along the floor and it requires a steady force of 22.5 newtons. If you push it for 13.6 seconds, how much work have you done? Okay. Let's do a quick check. Work is force times distance. Is there a force in this question? Is there a distance in this question? And I'm imagining the situation. Are they in the same direction? I think they are. You're pushing horizontally. The box is sliding horizontally. So I think we'll take a little shortcut. We'll go straight to the equation. We'll say force times distance, 22.5 times 13.6. What'd you get? 306 even? Oh, that's nice. 306, and the unit for work is joules. Now, some of you might also know, wait a minute, Mr. Dewick, I thought energy was measured in joules. You might have learned that in Science 9. It is. Energy is the ability to do work. If an object possesses energy, you can get it to apply a force over a distance on another object. So they are the same units, a slightly different concept. Dylan pedals his bike up a 19-meter-high hill that is 91.4 meters long. The mass of the bike and the rider is 65 kilograms, and the bike requires a steady force to continue up the hill. Suppose Dylan used a rope to climb vertically up the back side of the hill. Suppose he followed that path right there. How much work will this require? Well, when you're climbing a rope, draw the free body diagram on you. What are the forces acting on you? Get the obvious one. And I guess for you to go up at a steady speed, the force that you're applying up must be exactly the same as gravity. So there is a vertical distance, there is a vertical force. We're going to say, okay, work equals force times distance. You know what? Climbing and lifting are really the same physics as far as I'm concerned. It's again going to be mgh. What's the mass of the bike and rider? Now, I realize it's a bit silly to say, well, he's carrying the bike while he's climbing the rope, but humor me for a second. The mass is 65. G is 9.8. 19. And this one we're not going to round off. What do you get exactly? Mackenzie, what'd you get?
12,103.
12,103? Not rounded off, it worked out even? Oh, nice. 12,103 joules. How much work does Dylan do riding his bike up the hill? And this is why work and energy are so nice. When you climb up a hill, which force are you doing work against? Why is walking up a hill tougher than walking in a straight, flat surface? Gravity. The fact that work is a scalar, it doesn't care about the path that you took to get there. Whether you climbed straight up, whether you used a ramp, or even if you had kind of a curvy thing like that, or if you did, no matter what, you're doing work against gravity. You're doing the same amount of work in every one of those situations. In every one of these situations, you are doing 12,103 joules of work. However, riding up a ramp, because the distance that you're going up the ramp is longer, the force can be smaller. This is the definition of what we call a simple machine. A machine in science is something that increases distance and allows you to decrease force. If you've ever used a jack to jack up a car or a vehicle, you want the car to go up this much, but you have to move the jack handle up and down way more times. You move the jack handle through a way bigger distance, but you have to apply a smaller force because you can't lift the car on your own. So using our answer from part A, how would I get the F by itself? Because it wants me to find the force. So another equation for force, not on your formula sheet. It's the work divided by the distance. It's going to be 12,103. But that distance has to be in the same direction as the force. Since we want the force required to pedal up the hill, which distance are we going to use? Not the 19. What? 132.4. There is a chance that I may be showing how old I am. When I was a kid, my first bike that I got when I was 5 or 6 years old didn't have gears. And I'm learning that many of you, perhaps your first bike had gears, I don't know. And I learned very quickly that if I wanted to ride up a steep hill, I couldn't apply enough force. I either had to get off and walk, or I figured out actually I could increase the distance. And what I learned to do if I was going up the hill, imagine this is a lousy side view, I would zigzag up the hill on my bike. And I learned if I went back and forth like that, sideways, turn around, sideways. I was increasing the overall distance to way longer. That allowed me to reduce the force because I had to do the same amount of work to get to the top of the hill. And the work was whatever my mg was times the height of the hill. Maybe you figured that out when you were 5 or 6, that to go up a steep hill, you can zigzag up it as well. It's why we do switchbacks for trails and things as well for hiking. It's the same principle. We can't go up the steep one too hard on people. They can't exert that big a force. We'll put some switchbacks in the trail. We will increase the distance, thus lowering the force. We will take advantage of this equation here. If you're stuck with a certain amount of work and you can't apply a big enough force in the distance that they gave you, bump the distance up, lower the force. Some of you are just, I never thought of that. Or maybe you all got, maybe your bikes all had gears. I've noticed, I've mentioned this a few times, and the kids have looked at me blankly. It was in my neighborhood, it was common knowledge, and maybe it was because also I grew up on a street that had one massive, massive hill you had to get up to get to your friend's house or whatever. And so, okay, I'm either walking or I'm going to pedal it. If I'm going to pedal it, I got to zigzag back and forth. Turn the page. So this is one of the lovely characteristics about work. It's a scalar. It doesn't care about how you ended up at your location. It only cares where'd you start, where'd you end up. It doesn't care about the path in between. How much work would it take for Dylan to ride to the top of this hill? 12,000. Was it 12,103? Because it's the same height, 19 meters. It's the same amount of work done. Here, it would probably be a little easier because you've increased the distance. You would have to exert less force. It would take you longer. This is also how stairways work. Really, if we wanted to, we could make every stair a ladder. And the work that you're doing, the amount of work that you're doing is that. But not everyone can climb a ladder. Certainly if you're carrying things, it's awkward to climb a ladder. So instead what we do is we lengthen the distance, lower the force. What takes more work, lifting a 25 kilogram mass to a height of 4 meters, lifting a 50 kilogram sack to a height of 2 meters? Oh, how are they the same? Why? Because mgh equals mgh. 25 times 9.8 times 4 is the same as 50 times 9.8 times 2. You know what? Half the distance and twice the mass is going to give you the same amount of work. Yeah, that works. That worked. Nothing. Okay. Tough audience. That only is useful for a constant force. What if the force is not constant? What if it's changing? Chantal, work is what times what? What was our new equation today? You're going to get 3 different ways to think about work over the next few days. And what you're going to do whenever a question says, how much work? You're going to run through a checklist. And the first thing you'll try is, work is what times what? That only works if it's a constant force. If it's a changing force, work is also the area under a force versus displacement graph. How will you know to use this method? The question didn't give me a force, but it gave me a graph. It's kind of a Captain Obvious. Chantal, what does example 7 want me to find? Keep reading. How much work was done in, keep going. From where to where? Okay, let's all of us take our pencil. Let's put a little dotted line to 2 meters and a dotted line to 5 meters. And I guess, first of all, don't write this down, just notice, can you see, Chantal, the force isn't constant, it's getting bigger. It starts out too high and it ends up at 8 newtons, so it is a changing force. So I can't just go, oh, the answer is 8 times 5, 40. Okay? It's going to be this area here. What shape is that? This has 2 sides that are parallel and 2 that aren't. It begins with a T. Not a triangle. It's got 4 sides. Unos, dos, tres, cuatro. No triangle. What shape is this? What do you call a shape that has two parallel sides? Do you say triangle? Yeah, no. Begins with a T, though. Colby. It's trapezoid. What's the formula for the area of a trapezoid? I always ask, and there is a candy if anyone knows it. It's obscure, but it's taught often in other countries in their curriculum. Does anyone know? And for the first time in a long time in my Block Cs, I did give out a candy. Does anybody know the formula for the area of a trapezoid? I'm looking right now at my ESL students or my students from other countries, probably. Anybody know? There's a reason you don't. I know because I'm a nerd. The reason you don't is it is redundant. You don't need it because any trapezoid, two parallel sides, two non-parallel sides, can be broken up into a rectangle and a triangle. And you have done the area of a rectangle in your math careers, and you have done the area of a triangle in your math careers. And so although there is the lovely equation for a trapezoid, I think it's still on the board behind me over on my right. Is there one there that has a 1/2 and an a plus b and stuff like that on the whiteboard there, hidden kind of sort of? That's the formula for the area of a trapezoid. It's the height times the short side plus the long side divided by 2. But whatever. So we're going to find this area. Chantel, what shape is area 1, that bottom one there? I'm looking for it begins with letter R. So I'm going to, let's see, I want to be organized and lazy. So how about A1 for area 1? I usually use Roman numerals to label areas just so I know that it's not an actual number. How do I find the area of a rectangle? What's the length? Look at the graph. Starts 2, goes to 5, 3. What's the width? Not 1, be careful. What's the scale going up by? 2s? In your head, Chantel? Yo, 6 is right. Then we're going to find the area of the second shape, which is a triangle. What's the equation for the area of a triangle? Yep. I typically call it base times height divided by 2, but you're right, it's half a rectangle. In fact, I've seen some teachers, they teach the rectangle as base times height, because that also then works for a parallelogram. And then they teach the triangles half a rectangle. How do you take half of something? Divide it by. Or you may have seen it phrased as 1/2 base times the height. Okay, so let's look at this triangle. The base is that length right there. I think 3 again, yes? Now the height is that side right there, which is not 8. It peaks at 8, but how low does it go? 2. So what's the difference? What's the height, Chantal? Divided by 2. Could you do that in your head as well, please? Yes. 9. Yes. No, you missed that totally. Wow. I should have said yeah. Okay. You said 9. It's a German student say. No, nothing. In your head, 6 plus 9. Yep. This is work. What are the units? Now, you don't know yet, but if I know how much work has been done on an object, with a bit of cleverness, I can figure out how fast it's traveling, or how, if we're looking at rockets, how high from the Earth it'll go. We're not going to look at that this year, but this is a very, very useful thing to have. So, work is what times what, Chantel? The very force times distance. Work is also the area underneath a force versus distance graph. If a question asks how much work, the first thing I'll check is there a constant force and is the distance in the same direction? And if there isn't that, did they give me a force versus distance graph? If they didn't, not a luck. So we have 2 definitions for work. What was the first one you said, Chantel? Work equals... This requires a constant force. or work equals the area under a force versus distance graph. F is on the y-axis in newtons. D is on the x-axis in meters. Turn the page. Couple more, we're done. Did I go too fast, Louisa? Sorry. Got it okay? Yeah? Okay. Example 8. Gagan, what does 8 want me to find? Oh! Force times... Ooh, I can't go force times distance because the force starts at 20 and ends at 30. This is not a constant force. This is a changing force. What's my second definition of work? It's also the area underneath a force versus distance graph. They gave me a force versus distance graph. So we're moving at 10 meters. I guess we're going to go... I guess it's this area here. Except, it's a trapezoid. Right, Ethan? That's 4 sides. What's the area of a trapezoid? I don't know. Never bothered learning it because I can turn any trapezoid into a triangle and a rectangle. For some reason, I tend to do the rectangle first, probably because it's the easiest equation and gets the juices flowing. You don't have to. I don't care how you label them. So, area 1 is going to be length times width. Is it 10 times 20? Yeah. Yep. In your head? You're multiplying 20 by 10. Just add a 0. Yes. Area 2 is going to be base times height divided by 2. The base, I guess, is still 10. The height is the trickier one. Oh! Is the height also 10 because it starts at 20 and goes to 30? Yeah. Don't forget divide by 2. 10 times 10 divided by 2 in your head. Thank you. No hesitation there. Can you add these together in your head? How much work was done? Yep. If you knew the mass of this object, you would actually be able to calculate how fast this object was moving after you'd pushed it for 10 meters. We'll get there. Coming down the pipe. Is this the last one? Yes, it is. So, let's jump up a notch. Jump up a notch. It says 124 kilogram box is being pushed along a floor that has, a mu, a coefficient of friction. What's mu? I don't know. What's mu with you? Of 0.25. The person pushing applies a force of 525 newtons over a distance of 22 meters. Okay. Cool. I think. Maybe. Ethan, what's A want me to find? What's B want me to find? What's C want me to find? Okay. I don't think these are all the same answer. So now that I've noticed that I have to be a bit more careful. What's A want me to find? I think the work done by the pushing is going to be the force of the push times the distance that it moved. I think the work done in overcoming friction is going to be the force of, want to guess? Yeah. Divided by the distance that it was moved. And we'll talk about C in a second. Okay. What force was this person pushing with, Ethan? I'm good with that. Seems to be constant. I don't see any hint that it's a changing force. What distance did he push it for, or she push it for? And that seems to be in the same direction. I'm imagining someone sliding stuff around on the floors. How many joules of work did this person do? Is that right, folks? Okay. That's not how much work was done on the object, because now we brought friction in. Some of this work went into overcoming friction. And so you have correctly said, I'm pretty sure I want to put the force of friction times 22. I don't know friction. You know what? This is a job for a free body diagram. How about over there? What are the forces acting on this object? Get the obvious one. What else? And then there is an applied of 525 newtons to the right. And I'm thinking a little friction this way. I remember doing this like before spring break. Wow, this is a while ago. How can I calculate friction? Or as I've often said, friction is what times what? So this is going to be mu times the normal force times distance. I don't know the normal force. Oh, but look. I don't know the force the same size as the normal force, because it's not sinking to the ground like quicksand. It's not flying jet like Superman. So you're telling me this is going to be mu m g d. It's going to be 0.25, 124, 9.8, 22. .25, 124, 9.8, 22. Do you get 6683.6? I'm going to write this whole thing down without rounding off, and you'll see why in a second. 6683.6. And this is wrong. What? For candy, can everybody see why this is wrong? At the very beginning, I said work was what times what? No, work was what times what? But then I said the force and the distance had to be in the same direction. Which way is the distance? Which way is friction? What would be a good way to show opposite direction? Now, this negative isn't actually a direction. What this is saying is you lost that much work to friction. You did 11,500 joules, but of that 11,500 joules, you lost 6,683.6 joules to friction. So what's the net work? How much of your work went into making this box speed up? It's going to be 11,500 joules, take away 6683.6. Oh, missed a zero. And I'll use my answer button because I can. You get 4816.4. And we'll talk more about what this means, but the short answer is that much there, that 6,683.6 joules lost energy, negative lost energy. Where did it go? Went into heating up the floor. Which is why when you rub your hands together, for example, you can feel that you're generating heat. Some work is being done against friction. What's your homework? I think I assigned almost every question, but let's double check. Maybe I did assign every question. Yeah, I assigned every question. So 10 questions. This is also a chance a large number of you are still missing assignments from last unit. This is a chance for you to kind of maybe sort of get some of that caught up as well. Okay? So my students have pointed out that we are in a hurry. Did you read me that, or did you round off? I won't ask. It's 11,550 there, and so it's 11,550 there, and so what do you get here? $4,866.4. Is that right? Okay. Thank you.